All right, this is the second video for section 10.3. We're moving on to talk about polar curves and what they look like. So the graph of a polar equation, r equals f of theta, consists of all the points P that have at least one polar representation that satisfy that equation, exactly the way you think it would work. So let's jump straight into an example, the most common example. What if we just had the simple equation r equals 2? There's no theta in there at all. This would mean everywhere on the polar coordinate system where you have a value of 2 for r and theta doesn't matter. So if you think about tracing around every point that has a radius value of 2, this would create a circle, as you can see in figure 6. So every single place on this pink circle, the r value is 2, regardless of theta, since theta isn't in the equation at all. So r equals any sort of constant is a very quick way of graphing a circle in polar coordinates. And we'll see a little bit more later on about how to graph polar equations using your calculator. So what about something a little bit more complicated? Let's look at r equals 1 plus sine theta. Now I have to tell you, the first thing I would probably do is open up my calculator and graph it there, and we'll do that again in a little bit. But let's talk about it from a philosophical, I guess you could say, idea at first. Now the easiest way to understand what this is going to look like is to start out by plotting this function in Cartesian coordinates, pretending that theta is your x and r is your y. And that is the graph you see on the screen here. A standard sine curve shifted up 1 unit because it's sine of theta plus 1, okay? And we only graphed one period of the sine curve from 0 to 2 pi. Now, looking at that graph enables us to figure out, well, what would r be as theta changes? Because remember, the polar coordinate system is using r and theta. So if we go back and look what's happening to r as theta goes from 0 to pi over 2, you can see r starts out as 1, and as we go towards pi over 2, r grows to a value of 2. So again, as theta goes from 0, which on a polar coordinate system is the x-axis, pi over 2 gets us up to the y-axis. So as theta grows from 0 to pi over 2, r moves from 1, which is you can see where it starts out from, and grows to 2. So when theta is pi over 2, which looks like the positive y-axis, r is 2. So you see a part of a curve getting created here by the first part of that sine curve. If we move on to the second half, if we go from pi over 2 to pi on the normal xy coordinate system, you can see that r starts at 2 and goes back down to 1. So it's almost doing the exact opposite, or it is doing the exact opposite of what the first part of the curve did. So of course, on the polar coordinate system, you see that as well. It's starting up here at pi over 2, and the angle moves down to pi, and r has to pull back from 2 up here at pi over 2 back to 1, which is why it has to curve back in so that r comes back to 1. Remember, r is the distance from the pole out to the point, pole being the origin. Okay, so we've covered from 0 to pi. What about from pi to 2 pi? Well, from pi to 3 pi over 2, what happens? R starts out as 1 and goes down to 0. So our curve starts at pi, where r is 1, and by the time we're at 3 pi over 2, which looks like the negative y-axis, r has to come into 0, which means it pulls all the way back into the origin. And then again, from 3 pi over 2 to 2 pi, it climbs back up to 1, doing the opposite of what it did before, which completes our curve. You can see here on the right in figure 11D, the pink part. Again, we're starting with r equals 0, and then we have to end up with r equals 1, going from 3 pi over 2 over to 2 pi. So on first glance, before we saw the screen, you might have thought this was just going to create a circle. But instead, this bottom part has to pull into 0 to represent r equals 0 down here at 3 pi over 2. Now this is a special shape that we see pretty often, and so it has its own name, which you see at the bottom of the screen here. It's called a cardioid, which of course generates from the fact that it sort of looks like an upside down heart or a peach or whatever you want to pretend like that shape looks like. But the standard name for it is a cardioid. Very strange word, I know. Everyone can say it out loud now with me, cardioid. So again, it's called that because it's shaped like a heart. It's a special curve that we see pretty often. Okay, the remainder of the curve is drawn in a similar fashion, as long as you put the arrows, and it's going to just retrace itself. Why is that going to happen? Because a sine curve is periodic, and remember that after 0 to 2 pi, the shape it draws is the same over and over and over again. So our cardioid will trace over itself over and over and over again. And we sometimes call that a four-leaved rose because there are 4 different loops to it. And this ends the second video about graphing polar curves.